what I want to do today is just a very quick review in the next few minutes about what's going on inside that. And then we're going to look at a bunch of movies showing more about what's happening inside this system. So the review is looking at this image. Remember, there's red particles or small flocks that are the ones that never got very flocculated inside the flocculator. And their characteristic is that they're settling too slowly to be caught by the plate settlers. And so if we don't have a flock filter, they just go right on out the top of this tank and go on to the filter. So red guys are the guys that we would like to reduce their concentration as much as possible. And remember, at the beginning of the process, like if you were looking upstream from the flocculator, right, where the water's coming in, all the particles are red guys at that point. All of them are particles that would have just gone right through the sedimentation tank. So if this isn't clear, if you turn off the chemical feed, the coagulant at the beginning of the plant, then you don't make any flocks. You only have red guys, and those red guys go washing right through the flocculator, right through the plate settler flock filter system. Okay, that was red. The green guys, the green ones are flocks that grew inside the flocculator and grew large enough to be caught on the plate settlers. The blue ones are the ones that are made up of green ones that aggregated by rolling down, cascading, having an avalanche down a plate settler, and they combined, green ones combined into a blue one. And then the blue ones are able to settle fast enough that they actually hang out in the flock filter. As the water is going up, they're settling by gravity and just hanging out. And the blue guys have a little bit of flow that goes right through them. And that's how they act like a filter. Some of the water that's going up through the flock blanket goes right through those blue guys. And inside the blue flock, there are lots of clay particles and other things that are kind of held in place by the coagulant. And as a clay particle goes up through there, there's a chance that it can collide with one of those particles and stick and remain inside that blue flock and become eventually a blue flock with lots of red particles inside it. And as it does that, it becomes more dense, its fractal dimension increases, its porosity decreases, and so very little flow of water goes through it anymore, and hence it's not able to capture any more red particles, and so it ends up being useless. And we're going to go to this system where we actually make a little tiny little tank representing this inside the lab, and we're going to look at what happens inside that system. And we did this because there were things that we ran into in the field, in the water treatment plants in the field, where it didn't work the way we expected it to. And the thing that actually wasn't working right is we weren't succeeding in getting flock filters in the plants in Honduras, even though in the lab, we could make a flock filter in an hour. And we couldn't figure out what were we doing wrong with the geometry that in the field it worked and in the lab, that in the lab it worked and in the field it didn't. So we built this system, and we're going to jump ahead to look at what happens when it's working, and then we'll come back to what was the geometry that was messing us up and was making it not work initially. So first, what happens when it's working? So we're going to look at this, and we just started this the last time. And so I intend to play through this a couple of times. You could think about, why does the green graph stay relatively constant? The green graph is looking at the concentration of solids in the green rectangle at the very top of this system. The red one is from the red rectangle, and look at the red one. Right there it crosses, and you can see that the red line went up really, really fast as the suspension crossed that red box. Does that make sense? We're looking in the red box and we're figuring out what the concentration is. Okay, so that was one. Let's do it again. You can see that there are things settling out on the incline. There is some interesting behavior on the incline that I don't actually understand. And maybe it's a little bit dark, but you can wow, you can see that it looks like there'd be some interesting things happening at the very bottom of this. And you see that it grows quickly. Granted, the time is sped up a lot. We're at 14 hours right now, 15 hours, 16 hours. And you see the flock hopper kick into action right there. It's going to kick into action, and you can actually see the flock hopper filling up. Should we do that one more time? So notice that the blue line, which is the turbidity coming out of the tube settlers that are at the top of this, once the flock filter starts forming, those numbers start dropping. And so the blue line is dropping here. And that is because the flock filters are successfully capturing particles that otherwise would have gone right through the plate settlers. I'd just be happy to take any. Okay, I think I'm going to let you read that slide at your leisure because you don't like it when I read text, I'm guessing. So we'll go to the next one. So let's think about this for a second. What happens if we have a system that's up and working, and then what happens if I slow the flow rate down? So real plants don't always operate at the design flow rate. Matter of fact, they often don't operate at the design flow rate. And so if they don't need as much water, they operate slower. And then the question is, well, what happens inside this system if the flow rate is slower? So could you think for a second about what do you think would change if the flow rate through this system slows down? Oh man, that's hard. I should have asked this question later after we saw more videos. Maybe I'll come back to this. Unless someone wants to jump in with an idea, what you think might happen when you slow this down. Oh, and it's also good to try Monroe's idea of just go to extremes. What if you slow it down a lot? Then what's going to happen? Maybe you will see it. You've got this suspension of particles that you're succeeding in resuspending. Can you imagine what happens to the concentration of that suspension of flocks if the flow rate or velocity up through them decreases, slows down a lot? What happens to that concentration of flocks? You'd end up with a lot higher concentration of flocks in the flock filter. And that means that they're dropping down onto the incline part of the bottom of the sedimentation tank, and then sliding back down to where the jet reverser is resuspending them again. And that means it's actually harder to keep that system in suspension because it's much more concentrated. And so if you slow down one of these tanks too much, it will fail. The flock filter will actually collapse. So there's a failure mode, and it seems we have to think about what are we going to do about that. There is one nice option that we have inside an Agua Clara plant, and this would be not unique to us, but you should be able to turn off. You'll have multiple sedimentation tank systems in parallel, and you could always take one or more out of service so that the other ones keep on running at a reasonable rate. So that's one way to get around that problem. But I note here that we don't have the equations to describe this yet. So there's more work to be done. And here's another one. the operator would like to know what's going on both inside the flock hopper and also being able to see what's happening inside the flock filter. And you're looking at it from up above, and you could conceivably, and actually operators do this, if you shine a flashlight down between plate settlers, you can actually see down to the top of the flock filter. So that's one way that you can kind of tell what's going on. But it's awkward because this system is kind of buried in concrete underneath the plate settlers, and so you can't see it very well. Okay, so now we're going to talk about what we discovered about this jet reverser system that's at the very bottom. So this jet reverser is the key to make this whole system work. And it was invented in the labs at Cornell with that apparatus that I showed you by playing with various designs and seeing what went wrong. So this is our current design. There's a little 3-inch pipe at the bottom, very bottom of the tank in the middle. And the diffusers, the pipes that are bringing the water in from the flocculator, are shooting down into that half pipe. And that's what's causing the flocks to be resuspended. So here's a few videos for fun. The video on the left is we're testing out the design that we were actually building in Honduras. And the design in Honduras had a flat bottom with a diffuser just blasting flocculated water onto that flat bottom. And you see that it's not succeeding in making a flock filter. And there's a huge contrast with the one on the right, where it grows very quickly. And the one on the right has the jet reverser installed. So it's interesting looking at the one on the left, and look at what's happening right now. There's sediment accumulating in the bottom of the tank, and it's slowly working its way in. And it's almost like that sediment is like knocking on us and saying, look, if you made a little round thing down here, it would work. See that? Like the sediment is actually making the form that it needs to be in order for it to work. The problem with the sediment is that it's not stable. And so it keeps on eating away and then coming back. And so that system never works. And that explains why the plants that we built in Honduras that had flat bottoms didn't work. And so there was this great insight. You need a jet reverser in the bottom, where you're very much controlling which direction the water takes that you're injecting into the bottom of the tank. Here's some more videos of the same kind of problem. So flat bottom, centered and offset. And I have a colleague, Len Lyon, that I worked with for many, many years, and good friend. And we would be advising students, and we would essentially take bets, although there was no money involved, but we would essentially take bets about which system would be better. And then the students would do the experiment, and then unfortunately, one of us would be proven wrong and one of us would be right. And I felt like the world is beautiful, physics is beautiful, there are beautiful equations, axisymmetric is beautiful. So the best design here will be an axisymmetric system with a centered jet. And Len Lyon said, nah, he thinks it's going to be axisymmetric. He thinks it's going to be non-symmetric, that it's going to be better with the inlet off to the side. And guess what? He was so right. Off to the side, it's completely stable. It forms a flock blanket very, very quickly. And there's never any failure that shows up right at the bottom of this tank. Whereas when you're injecting dead center, that jet that you're injecting dead center, the jet can, with relatively little force exerted on it, can decide to go more into one direction than in the other direction. And what happens is sediment can accumulate on the one side more, and that will push the jet away from that sediment. And because that jet can be easily deflected, it's not always stable. And you can see that, like in the video right now, you see that the jet is kind of going more towards the left and less towards the right, because the sediment is coming in further on the right side. So it's better to not give the jet a choice and to put it in on the one side of the jet reverser, so that its only choice is to go around like this. I want to do this video, or this is an animation to help explain what's going on. So the inlet diffuser is bringing flocks from the flocculator, and they are going on up to the plate settlers. Eventually, some of them come back down as bigger flocks, and those bigger flocks, eventually, some of them land on the sloped part of the bottom of the sedimentation tank, because gravity is working everywhere. And so when they do, that slope is steep enough that they slide down. And then they slide into where the jet is coming up. So the jet reverser ends up, jet comes around the bottom here, comes up right here. And so it resuspends any particles, any flocks that are sliding down that incline. And then at this point, you should be asking, well, what about the other side of the tank? There's another incline. What do those flocks do? So we'll turn that on. So the flock on the other side does that. Goes down to the incline, slides around, and gets carried the whole way around the jet reverser.